large going on within the ARG that we cannot talk about yet, but
Spoiler.
a little bit about. No pressure, Ike.
Thanks. Yeah, so I'm Ike, and I'm applied scientist at AWS. Now, at AWS, we, of course, care about building correct and robust services. But as we all know, that's hard. So there's a couple of avenues we're pursuing. We're using more safe languages, such as Rust. And we're trying to use formal verification at an ever bigger scale. So as Dominic hinted, there's a verification project going on that we cannot yet talk about. But what I can tell you about is AutoCorrode, which is the formal verification tool we've been developing. So when the project got started, there were a couple of requirements. Firstly, there's engineers going to be working on this project. They want to write idiomatic Rust. So whatever tool we end up using, it needs to support a realistic subset of Rust. We are interested in proving functional correctness for this project, but not just that. We're also interested in verifying hyperproperties, such as non-interference of the system. And of course, we don't want to do this all by hand, so we are looking also for a tool with strong automation. The combination of doing functional correctness proofs and hyperproperties quickly led us to believe that, well, we need to be working in an ITP, in an interactive theorem prover. And the tools that were out there back then didn't really match our needs. So then we ended developing our own. This is AutoCorrode. So kind of a bird's eye view of AutoCorrode. It targets a fragment of Rust we call microrust. It's embedded in the Isabelle HOL proof assistant, and the functional correctness proofs are carried out in a separation logic. And to do these functional correctness proofs, we have a powerful and configurable automation tactic called crush. So it's a big effort, and there were several challenges along the way while developing AutoCorrode. I only have 15 minutes, so I cannot tell you everything. I will tell you about how we parse Rust or microrust in Isabelle, and I will talk about the automation that we have developed. So first off, microrust. Microrust is a shallow embedding of a subset of Rust in Isabelle HOL. By using a shallow embedding, we get the benefits of having Isabelle types for all of our Rust functions. But there's also some limitations, like, for example, currently we do not support while loops, and that is acceptable for our use case. And what we're going for here with this embedding is kind of to be eyeball close to the source code, so that the engineers that write their code see the same thing as the verification people verify. And for now, this translation is done by hand. We're trying to improve this in the future. So as an example, here's a Rust struct, time, with 3 fields, hours, and this gets translated to the next best thing in Isabelle, which is this data type record with, again, 3 fields. The types are going to be slightly different. So in Rust, you'll write U8, and in microrust in Isabelle, you'll write an 8-bit word. Now let's look at some function on these time objects. So in Rust, we can write this add minutes function, where the goal is we have a time object, we're going to add minutes to it, and if the minutes exceed 60, we need to carry on into the hours. So we have a mutable reference to a time object, self. We're going to add m to it. We're first going to check that we're not adding a crazy amount of minutes. We just want 60 at most. Then if self.minutes plus m fits within 60, we're just going to update the minutes field, return OK. And if it does exceed 60, we're going to add 1 hour and compute the minutes mod 60 and return OK. So it's a pretty simple function, but there already is some interesting control flow going on. So there's an assert. In the if, there's an early return. And there's this question mark operator on add hours. And that means that if add hours returns an error, we short circuit and also return this error immediately from add minutes, and will not update the minutes field. In Isabelle, in microrust, this looks like this. So it's going to be, again, add minutes. And I want you to look at the body first. So the body is going to be almost the same assert, same control flow. There's one change, which is this star operator in self minutes. So Rust will insert automatic dereferencing there. And in microrust, we need to be explicit. Now, of course, the types here are quite different. In Rust, you have this &mute, which indicates in the type system that you have exclusive ownership to write to self. This is not expressed in microrust, where you are working with this pointer to a time. And there you have to express the ownership on the specification. Another thing I want to point out is this strange bracket next to function body. This switches Isabelle from its regular parsing mode to a custom parsing mode that we've written, where you can basically write almost Rust. And here we use that Isabelle has a strong and very configurable parsing mechanism that we've used to be able to write Rust in Isabelle. So that's microrust. Now let me talk about the automation. So the goal here, remember, is to prove functional correctness. And we write this as follows. We have some program and want to prove that it satisfies some contract. The first step that Crush will take, it will SSA normalize the program, and it will turn this proof obligation of program satisfied contract into some weakest precondition style proof obligation. So we go from program satisfies contract to P being the precondition of the contract, entails, that's the long arrow here, the weakest precondition of the SSA normalized program with post condition Q. And this entailment here is a separation logic entailment. Now the rest of Crush is targeted at proving these kinds of goals. So separation logic entailments, usually with the weakest precondition as your goal. And Crush really tries not to be too clever. So what it will do for this weakest precondition is it's going to apply the relevant weakest precondition rule, and then it's going to do the obvious thing. So if you see the same premise as you see in your goal, you're going to cancel them in the separation logic sense. If you see a for all quantification, you're going to introduce that. One thing we really need to be careful with is schematics, meta variables, or existential variables. So if you need to prove an exists of something, you want to be very careful when instantiating this, because a wrong choice might lead you down a blind alley. So the cleverness of Crush, or the lack of it, is instead transferred to the proof engineer that can configure Crush to do the appropriate thing. So it's very configurable via attributes. This is also the natural way of writing Isabelle proofs. You add simp add to some tactics, and Crush will use this rewrite tool to continue. All right, so the next thing is a little demo. So this add minutes function we talked about earlier, I want to try and verify this. This is readable. If I should make it bigger, please shout. All right, so here's the same add minutes function. And let's first look at the contract I've written here. So the contract takes a reference to a time object. This log G I will not talk about in detail. Just pretend it's not there. It's just a reference to a time object. And then there's the time that's being pointed to. And this is the minutes being passed to add minutes. So the precondition is going to be self points to this T object. This is the separation logic points to. But we don't require just that. We separately require that first, that this argument m is less than 60. This is to make this assertion go through and not panic. And furthermore, we require that the time object t that's being pointed to is sane. So there's less than 24 hours and less than 60 minutes. Now the post condition is going to contain an if statement. So if minutes t plus m is less than 60, then we're going to hit this branch. Then we're just going to update the minutes field. So this self now points to the time object, the same time object, but we're going to update the minutes to be plus m. Now here, update minutes is a regular Isabelle update function that comes with the definition of the time object when you define it. So the second branch is when you do need to carry over into the hours, then you're going to update the hours and the minutes, but mod 60. And if that doesn't fit, then we will return an error. And separately, the precondition still holds. So we don't make any changes, is what this is saying. Now let's look at the proof. So we start with minutes satisfies minutes contract. And we'll first call crush boot. So this will SSA normalize add minutes and bring us to this weakest precondition. So you see here, self pointer entails the weakest precondition of this SSA normalized program. Let's see what happens if we call crush. We see now we have 3 sub-goals. So we have some side conditions that still need to be solved. And the first goal is still this separation logic entailment of the self pointer. And we, so that automation stopped at the call to add hours. And this is because crush is not aware of the specification of this add hours function. So if we look at add hours, it says, as you expect, there's a contract, but here I proved a specification for add hours. So we want to use that. And we can tell it to use it as follows. So now it's going to get a bit further. It's going to say, okay, now I need to prove the precondition of this contract, but I don't know what this is. So this is not unfolded by default. You can set it up that way, but I haven't right now. Now it's churned through the entire add minutes function, and there's three remaining proof obligations. So there's this minutes t plus m is less than 256. And this is because we are doing this addition here, and it's on 8-bit words. So we need to show that this actually doesn't overflow. And this turns out to never happen because of the precondition we've set up. But importantly, this is not a separation logic goal anymore. This is just a pure goal. And we can hand this off to Isabelle's solver for these kind of goals and complete the proof. And now it's interesting to see kind of what's going on under the hood. So under the hood, crush is really kind of applying the basic weakest precondition steps. And we can see that by using stepwise. So the first step here is going to go, hey, there's an assert. What's the rule for assert? Well, you need to prove that this can never go wrong, that this assertion holds. And then you need to prove the remaining part of the program. Step 2, we get rid of this first obligation. Then let's step a bit further. Right, so now we've stepped a bit further in the program. We've passed this assert, and now we're doing this dereferencing. So the next thing we need to show is the weakest precondition of the call to the dereference operation. And the precondition there is going to be, of course, another points to, which we need to cancel now. So that's what crush will do with another step. We lose access to the points to because we've used it to prove a part of our post condition for our goal. Then there's pure goals remaining, which can be discharged. So this just gets rid of this first pure thing we need to prove. And then there's a for all quantification next, which will be introduced. And then after another step, we get access to our points to again, now that we've dereferenced. We've used our points to show that dereference is okay, and we get access to it in the post condition. So another thing is you can step star to just do all the steps, and then it will print out all the almost 200 little rules it applied to get to the post condition. Another interesting thing you can do is you can, suppose we haven't proved add hours spec, we can inline actually that function. It will still go through. So we get a different set of proof obligations at the end. Apparently we need to simplify some kind of rule for the working with the time data type, but then still all the side conditions can be discharged automatically. Right, so let me get back to the slides. I talked about AutoCorrode, which is the verification tool we've developed for Isabelle. AutoCorrode works by translating the source code of Rust into micRust in Isabelle. And in Isabelle, we then developed separation logic automation via this crush tactic I showed you. AutoCorrode is open source available via this link and this QR code. And with that, I'm happy to take any questions.
Any questions?
Thank you for your talk. I have like a billion questions, but I will try to choose the main ones. Do you know lithium from Michael Samler? That's
Yes.
the base of refined Rust and refined C.
Yes.
How does AutoCorrode, like the base framework, compare to that?
I think it's similar in a way. From what I understand, lithium these days is a bit more, has been abstracted away from the refined C and is now very portable between these frameworks. I know it faces some of the same problems, like introducing existential variables. So it is quite similar in a way. This is in Isabelle. It's more focused towards our verification goal. And what I do know is that, or what I do suspect is that being in Isabelle is going to help somewhat with the performance of these proofs, since in my experience of using these kind of tools, Isabelle is quite fast at these kind of things, being not in a dependent type theory.
That makes sense. And next question is, what do you have unsafe code, I'm guessing,
Yes.
somewhere, because you use separation logic. And how do you deal with the type system and lifetimes and lifetime
Yeah,
logic?
so the Rust types, they don't live in the micro-Rust anymore. So that means we have to do a bit more work, but it also means we can deal with unsafe code, since we're passing around pointers and proving that we have the correct ownership of those pointers when we need it. So yeah, does that answer your question?
I have more, but I will ask later.
Okay, cool.
Can the next speaker come up and prepare, please?
It's the same people.
So perhaps you have already answered this, but I'm not quite sure. What do you do about unsafe code? And does your tool, does it
AutoCorrode.
need to understand what is happening with borrowing? Or does it just trust the compiler data and everything?
So we don't trust the borrow checker. We show that the code is safe, I guess, in a different way by passing around the points to assertion when we need it. And so
Subset of what trust compiler is.
yes, it's definitely a subset. And so unsafe code, when it basically is a no-op in the AutoCorrodes, because we prove safety in this other way, because we pass around these points twos in the proofs. So we don't rely on the borrow checker, is another way to say it.
For unsafe code, that means you cannot assume that the code did anything. So if you need to have user library with W lists, and you call it, then after you call it, you know nothing.
No, if this were the case, then we would verify the unsafe code from the W-linked list implementation.
One more question, Stefan. Thank you for your talk. I have a question about the new static. So that static, could Sledgehammer search for that static automatically, or is there any existing other stuff that can try to don't write it manually?
So currently, Sledgehammer will not do crush proofs for you, and I figure that it'd be a bit hard to set up. We use Sledgehammer to discharge like the pure proof obligations that are spawned sometimes. But the separation logic proof obligation, we use crush. We don't use Sledgehammer there.
Sure. Okay, thank you. Let's thank the speaker again. Our next talk is